Alright, how we doing today? Doing good? Okay then. So for today we will have our final video of the semester, well, with the exception of the review, and for today we'll just go over the second part of the computer assignment and then a couple little problems that I wanted to do. So actually before we do that, I did assign one final quiz that should, where is it? Click. As you can see, edited today, and what's that? Look at that. And right here we can find your little quizzy, and oh, look at that, click, nothing's there. So let's click on this and let's see what I prepared for everyone here. So I say, consider a stable linear time invariant system that can be described by the linear constant coefficient difference equations. That, where we have that and that. So the thing I'm asking from everyone is to determine the system function h of z and then the system zero input response. So remember from what we were talking about back in the let me see if I want to remember, from the Laplace domain, where I think it was the derivative one, because the derivative Laplace derivative property. Is it derivative? Yes. Where basically the unilateral the Laplace derivative property states basically if you had the following d of n yt with respect to dt of n, you would convert all this into s of n and then big Y of s minus Sn minus 1 y of t is equal to 0 minus, then minus minus Sn minus n. Why do I put that? Because that's how we count n minus 1 up to s0 of d of n minus 1 y t is equal to 0 minus divided by t respect to time n minus 1. Remember that? So this is when we would include initial conditions. I will mark that down. ICs. So this would be 1 and then this would be 1. Remember that stuff from the Laplace transform? So same thing, however we're not using derivatives. So how do I explain this? Remember how when we were building these blocks, or okay, this is probably not the best way to explain it. So I want to let's do it, where we would have some y of t and then we would have this d dt, right? And then what's the derivative of y of t? It's just dy of t dt. Remember that? And then we would do all these state spaces and there would be initial conditions, right? So Laplace. There we go. Remember that? So this is the building block that we use in our analog systems, but what do we use in our digital systems? In our digital systems, no, let's use this marker. We use the following: y of n. Okay, and what type of blocks do we use? It's these little z to the minus 1s. Then what do we get at the output? N minus 1. All right. So what I'm gonna say is I think it's like the delaying property. It should be somewhere in the notes, delay or shift. Delay. I'm just gonna write this there. Question mark. For the unilateral z transform delay property, which states that if you have a form of y of n minus n, okay, what you're gonna memorize is the following. So the first thing that's going to pop out is this z to the minus n. Okay, don't forget that. Okay, and then you're going to put this big capital Z. And then it's not going to be a minus, it's going to be a plus. So it's going to be plus z, okay, minus 2, n plus 1 of y of minus 1. There we go. So why is it minus 1 and not minus 0 or 0 minus? So in the digital domain, well, we don't have any way of stating like previous states. Our previous states are this. This is our IC. Okay, that. So how do we do the next increments? You do it like the following. So you keep doing this plus z n plus 2, but instead of it being y of minus 1 minus something like that, it's going to be y of minus 2. You see the pattern? So if you keep going down, plus z to the n, so the negative n plus n, so that just results into a 0. Z to the power 0 is 1. Y of, okay, 0, 1. Okay, 0, 1, and I would guess, hold up. 0, 1. Oh, I got it. N minus n. I think so. So all this right here, I should probably use a different marker. ICs. 1, 2, and 3. See that? So this is what everyone's going to be memorizing for the exam, because there will be 0 input responses on this exam. So how are we going to prepare for that? We're going to do the following. Let's see. Anyone here? No. Let's see. There we go. So let's attempt the problem. And you're going to like this one. Oh. And I will put this on the side of my screen because I have the power to do that. And, wait, nope, not Matlab. I'll show you that later. Okay. And now let's write it down. Black marker. Okay, let's try it. Y of n minus 1, 1 divided by 6, y of n minus 1, minus 1 over 6, y of n minus 2, okay, is equal to 3x of n minus 1 over 3, x of n minus 1, minus 1 over 6, x of n minus 2. Cool, okay? So, looking at all these delays, right, or y's and this, right, we're going to convert this all into the z domain. So, if you're taking the z transform of y of n, what's that equal to? Hard? Now, minus 1 over 6, and then this is where the fun starts. We're going to look at this term, okay? And then since we have a n minus 1, following our little rule, and I should probably do it like this. There you go. We're going to do z to the minus 1, because that's our delay. That's the maximum delay right there. Y and z. There you go. Z transform of y. Then plus, okay, just for minus 1 plus 1, okay? See that? And this will just turn into 1. Y of minus 1. So n is equal to minus 1. All right? Easy? And that's it. We're done. Hooray! Now for the next term. Let's use this marker. Boom. Okay. And what do we have? Minus 1 over 6. And then we have z to the minus 2, okay? See that? Because we have this minus 2, okay? And then the z transform of y plus z to the minus 1. Y of minus 1, okay? Then plus, you see the pattern, minus 2, minus 1. Then that should be 0 to 0. Y minus 2. Making sense, eh? Cool. And now we got to do the output or the inputs. And that should be that bad. So what's the z transform of x of n? 3x z. There you go. Easy. And now let's do the next one. Let's color code this a lot. Minus 1 over 3. And then we have one delay, z minus 1, x of z. There we go. Plus x of minus 1. And then the final point we got for today, minus 1 over 6, z to the minus 2, x of z, plus z to the minus 1, x of minus 1, and plus z to the minus 2. Oh, got ahead of myself. X of minus 2. Simple? Cool. So now the next thing we gotta do is start grouping stuff, and this is the fun part too. Let's use the dark blue marker. All right, you see this y, z term, this right here, and this right here? We're gonna pull them out, and then we're gonna try to group them in the following. So y of z, okay? Put this big bracket. We're gonna put a 1, because that's that first term. And then this term has a minus 1 over 6, z to the minus 1, okay? And then here we have a minus 1 over 6, z to the minus 2. Sweet. Then, how do we do this? Let's take care of the other term. It's okay. Minus, got this one, 1 over 6. I'm just gonna make this 1. There you go. 1 over 6, y minus 1, okay? And minus, that's what I was thinking about. So one thing I was looking at was, you see this y of minus 1 and then y minus 1, right? I was trying to do the following. Let me rewrite it. Maybe you guys will see it. Y of minus 1. So the initial conditions due to, well, the previous output, y n is equal to minus 1, is going to have the following. Minus, let's just put a plus, minus 1 over 6. That one right there. This one right here has minus 1 over 6, z to the minus 1. Cool? Then I think I should have, that takes care of this, and then we just have our final term. Minus 1 over 6, y minus 2. Cool? And now let's solve for the output, just grouping stuff. So our output has this term, and this term. We're just pulling out all the x of z's. So x of z is going to have a 3 minus 1 over 3, z to the minus 1, minus 1 over 6, z to the minus 2. Cool? And then, let's just finish it. And then, okay, let's look at this minus 1. Should I use a different color? Okay. Minus 1 and a minus 1 plus x of minus 1. This marker is bad. Let's finish it. Oh, nope, doesn't want to work with us. Minus 1 over 3. Go. And then minus 1 over 6. Z to the minus 1. There we go. And then the final term we got to take care of is, let's use this marker. This last term, minus 1 over 6, x of minus 2. Cool? So then there's one more thing I kind of had to explain from the beginning, or maybe you guys already caught it, but the impulse response, the impulse response is defined as h of z is equal to y of z divided by x of z. Okay? So what do you see kind of right here? You see this y, then you see this x right here. If we just divide this, well, kind of. We're going to divide this term into every other term and maybe move these constants on the other side. Okay, I'll write it on another piece of paper. 2. Lots of work, eh? Don't worry. Dr. Steve's probably thinking about a second order. Well, that is second order. First order, I would assume first order. It's not going to be that tough. 3. So if I were to rewrite all this mess, let's see. Y of z of 1 minus 1 over 6, z to the minus 1, minus 1 over 6, z to the minus 2. And then I'm going to move some terms. Equals x of z, 3 minus 1 over 3, z to the minus 1, minus 1 over 6, z to the minus 2. Okay? And then let me take care of the inputs. Plus x of minus 1, minus 1 over 3, 1 over 6, e to the minus 1. Yeah, a lot of work, right? Minus 1 over 6, x minus 2, okay? And then plus, I'm going to be moving these output initial conditions to the right side of the equation. This is a plus, that's a minus, so that means if we flip on the other side, it should be a minus y of minus 1, 1 over 6, minus 1 over 6, to the minus 1, and plus 1 over 6, y of minus 2. There we go. A lot of work, right? And now, you see this term right there? It's divided into every other term to get the following. Y of z is equal to, let's do it right here. 3 minus 1 over 3, z to the minus 1, minus 1 over 6, z to the minus 2, 1 minus 1 over 6, z to the minus 1, minus 1 over 6, z to the minus 2, x of z. Okay? And I'm going to use the other marker, plus, and I'm going to write it the following. X of minus 1, minus 1 over 3, minus 1 over 6, z to the minus 1, minus 1 over 6, x to the minus 2, minus y minus 1, minus 1 over 6, minus 1 over 6, z to the minus 1, plus 1 over 6, y and the initial at minus 2. All this divided by 1 minus 1 over 6, e to the minus 1, minus 1 over 6, e to the minus 2. Whew. And we're done. Is that cool? Any questions about that? Chat? No one's in the chat. Yeah, don't worry. So then the next thing I mentioned in this little quizzy I got for y'all is to determine, well, h of z and the zero input response. And then just leave them in terms of z to the minus 1. Don't do anything crazy. So let's see. So for the following, as you can see, you see this y of z and this x of z. So you see this x minus 1, x minus 2, all these previous outputs and previous inputs. Suppose all your ICs, initial conditions, were all set to 0. What happens to this? It's all gone. So that means if you were to put this x over here, see what I'm going for? So that means this right here is your h of z, your zero state response. So if you have 0 states, that means what's your response to, well, 0 states and just this input. Okay, you're just looking at the impulse response itself. Impulse response. Impulse response. Okay? Well, what happens if you wanted to do a 0 input response? So that means x is 0. So that means what happens when, what's the z transform of a 0? It's just 0. So that means 0 times this is 0, and then that just goes away. What are you left with? Ah, yeah, the states. So that means all this right here is h z I r of z, which is your, well, yeah, ZIR. Okay? And then what happens when you add both of them together? You get the total response, which is basically, if you wanted to do this for fun, H total is just equal to H of z plus H z I r of z. Okay, and based on the properties of linearity, all you do is just, well, you can solve for this, you can solve for this. Well, solve for this using whatever input, so a step response, an impulse response, like sinusoidal response. And then this right here is just, well, just what do these states do to your system? Add them together, linearity, done. Cool, right? And now the other thing I ask is to plot the region of convergence. So we will do that on another piece of paper. Okay. 4. So I ask for, let me see, pull that puppy out. For the zero state response. So we're just gonna purely look at this term right here, okay? Oh, you can't see that. There you go. We're gonna look at this term right here. So if you wanted to, I'll give a really good one. H of z is equal to 3 minus 3 z to the minus 1 minus 1 over 6 z to the minus 2 divided by 1 minus 1 over 6 z to the minus 1 minus 1 over 6 z to the minus 2, okay? Let me see. Well, one trick I'm about to show you all is the poles. So you could either do the following and do the, let's see, poles or something like that. Pole is equal to, x is equal to positive 1 over 6 plus or minus the square root of 1 over 36 minus 4ac minus 1 over 6 all over 2, right? You could do that, right? But there's an easier way. For this will technically get you the right answer if you want to. The other way I was thinking about is, you see these poles right there? Or maybe let's look at another number. Okay, let me just try this one. Plus, it's gonna give you 4 over 6 is gonna give you, actually let's keep it in that terms. 4 over 6 and times the entire thing by 6. 4 times 6 is gonna give you 24 over 36. That means you're gonna get 25 plus or minus 1 over 6 plus or wait, plus square root of 25 over 36 by 2, which is going to give you 1 over 12 plus or minus, well, what's the square root of 25 and the square root of 36? You're going to get 5 over 6 divided by 2. It's going to give you 1 over 12 plus or minus 5 over 12. Your final answers are going to be either 6 out of 12 and so minus 4 over 12, which correspond to 1 over 2 and minus 1 over 3. Oh, there we go. See that? Easy. I was going to try and show you another way. You can like kind of cheese this in a way. If you think about it, what I was going to say. Should I show you that? What two numbers multiply to 6? And you realize, oh, you have 2 and 3, right? You can do 2 times 3 is equal to 6. But if you were to do 1 over 2 and 1 over 3, and which one's going to have the minus sign, because this one's a minus, which one's bigger? This one's bigger, okay? So that means you have to put a minus right there, okay? You would put a minus. And then that's how you would play it. That's if you wanted to really cheese this problem. But if you want to do the hard way or long way, it's not hard. You can't. Don't mess this up. If you're getting 1 over 17 or 47 divided by 36 or something like that, then I would check your answers, okay? He's not going to give you hard poles. It's probably going to be really trivial poles, okay? These are nice poles, and it's stable. Okay, and for the zeros, I guess we can do a separate methodology for that one. Yeah, let's try it. 0 is going to equal 1 over 3 plus or minus the square root. Should I? I'm going to rewrite the zeros because I'm getting OCPD'd about this. 1 minus 1 over 9 z to the minus 1 minus 1 over 18 z to the minus c. Okay, there we go. Okay, rewriting. Right. Okay, now I'm going to do this. 0 is equal to 1 over 9 plus or minus the square root of 1 over 81 minus 4 for 18 all over 2. Oh gosh. It's equal to 1 over 18 plus or minus the square root of, what's a good number that fits into 18? Should we use Matlab? Okay, 18. Well, if you multiply this one by 18, well, 81. I don't want to do that. Yeah. So I made this problem for you guys using Matlab. And what I'm about to say is you can use roots of 1 minus 9. Actually, not even that. 3, 1 over 3 minus 1 over 6. So punching this into Matlab, and I'll show you this. Matlab. Oh, there we go. Clear all. CLC. And I will show you the following. Boop, boop. So roots of 3 minus 1 over 3 and minus 1 over 6. Boom. Yeah, those are not that. I don't like those. And actually, let's confirm the other one. So we have a 1 and a 1 over 6 and a 1 over 6. And yeah, that looks just like our poles, you see? There you go, 1/2 and minus 1 over 3. Cool? Yeah. All right, so I'm going to copy those numbers. Let's do the following. Okay, can you see that? 0.2977 and minus 0.1866. If only these were fractions. But now that we found our poles and zeros, now we can draw a region of convergence. But the region of convergence isn't determined by the zeros, it's determined by the poles. So if you really wanted to figure out a correct way, let's draw our little pole right there. And let's use this marker. I like this marker a lot. Okay, there we go. There we go. You like that circle? There we go. So we have a pole at 1/2, which means we're going to do the following. Bang. Easy. 1/2. Okay. And then we have a pole at minus 1 over 3, which means it's going to be right here. Minus 1 over 3. Okay. And now for our zeros. So this 0 is going to be at 0.29, which is less than 1/2. So it's going to be somewhere right here. Okay. That's this guy right there. And then this minus 0.18 is going to be in here. So we have two zeros like this. Cool? All right. So that means this is what we're going to see. Okay. Now the last thing is, okay, which pole is greater in terms of absolute value? So if you remember, absolute value, which one's greater? 1/2. Okay, so we're not going to draw it on the 1/3. It's going to be on the 1/1/2 because this is the largest pole. So that means if we were to draw the following, there you go. And to make it a stable system, we would draw it going outside. Should probably use, yeah, let's just use this marker. So it's going to go like this. Cool? And that is our ROC. Sweet, right? Perfect. And now, that's our region of convergence. But what's the next part? Because that's what I'm about to jump to. Boom. And now it says determine the system's impulse response. So that means we're going to go back into the time domain. So now that we have all our information, both the poles are going to be right-sided functions because they got to include the imaginary axis. If the pole was outside, that means it would have to be a left-sided function, which means you would have to like invert it in a way. Maybe I'll talk about that at the end. But now we know what to expect from our actual impulse response. And I will show you that on the next page. Okie dokes. And don't worry, I'm going to prove this in Matlab too. Aha, there we go. So, what we're gonna do is we're just gonna look purely at the impulse response. 3 minus 1/3 z to the minus 1 minus 1/6 z to the minus 2 divided by 1 minus 1/6 z to the minus 1 minus 1/6 z to the minus 2. Okay? So to solve for the impulse response, we want to get this in a form like residue 1 divided by 1 minus pole 1 z to the minus 1 plus residue 2 1 minus pole 2 z to the minus 1, etc., right? That's what we want. So what do we have to do? Partial fraction expansion. TL fraction expansion. Okay? So what we're going to do is the following. So for your exam, okay, there's two ways you can do it. You can either, well, if you want, you can multiply the entire thing by z/2, like turn all these z's into positive power coefficients. You could do that, but I'm going to keep it like this. I'm going to show you what to do and what not to do. Okay, I'll show you. So you're going to see it written like this, okay? But you're not going to do that on the exam. You're going to write it this way. Minus 1/6 z to the minus 2, okay? Minus 1/3 z to the minus 1 plus 3, okay? We'll do the following. And then let's grab the other marker, like this marker. And we're going to write it the other way too. So minus 1/6 z to the minus 2 minus 1/6 z to the minus 1 plus 1, okay? So why did I write it like this and not like this? So if you were to do the long division and start here, that's not what we want, because else you're going to get a 3 on the top, and that's not what we want. Don't worry, I've been through the pain. I accidentally was multiplying this to this first. No, you don't multiply the coefficients first. You multiply this z. This is your, well, not highest power, but it's the power that kind of really matters. We want to take care of these guys. The coefficients, who cares? Unless you take it all to the z to the positive 2. So looking at this term and this term, how many times does this fit into this? Just once. So that means this times this, and I'm going to put a big minus. It's going to give us minus 1 over 6, okay, z to the minus 2, minus 1 over 6, z to the minus 1, plus 1, okay? And now subtract. I don't like that marker. And then this term and this term cross out to give us that 0 term. And then this becomes, well, if we do it, plus, 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 minus, okay? So this right here is 1 over 6, and I'm going to rewrite it as 2 over 6, okay? So that means minus 2 over 6 plus 1 over 6 is going to give us minus 1 over 6, okay? And then this is 3 minus 1 gives us 2. Cool? And that is our leftover parts, which means h of z is equal to 1 plus 2 minus 1 over 6 z to the minus 1. And then would it bother anyone if I did this? 1 minus 1/2 z to the minus 1. 1 plus 1 over 3 z to the minus 1. And why did it, if that bothers you, nope, we got this from the beginning, the hand calcs we did. So our 1/2, that's our pole. This is what's going to make the thing unstable. How do you make it unstable? Well, you do this. So that means if you punched in 2 into here, that's going to give you, okay, if your pole is at 1 over 2, z is equal to 1 over 2, that means z to the minus 1 is 2. So that means if you replace the z to the minus 1 with a 2, 2 divided by 2 is 1, 1 minus 1 is 0, infinity, okay? Same thing with this, okay? How do you make those infinities? See? Easy, eh? And then there's a rule, like if you see like a number here, this basically tells you your pole. And if you see a minus sign, then that means it's a positive pole. And this plus gives you a negative pole. So a little trick to memorize if you want to. Let's see. So now that we have our poles, I'm going to rewrite it as the following. 1 plus a 1 minus 1 over 2 z to the minus 1 plus b 1 plus 1 over 3 z to the minus 1. Cool? And now we're going to do that heavy side stuff, but I got to do it on the other page because this is going to be messy. And I want to show everyone how I do it. And maybe you can copy this too. Oh. There we go. So looking purely at this term, 2 minus 1 over 6 z to the minus 1. 1 minus 1 over 2 z to the minus 1, 1 plus 1 over 3 z to the minus 1 is equal to a 1 minus 1 over 2 z to the minus 1 plus b 1 plus 1 over 3 z to the minus 1. To get the a coefficient, our pole is located at, so z is equal to 1 over 2, positive 1 over 2, okay? Don't forget that. And then our z to the minus 1 is equal to 2, okay? So that means we're going to place all the z to the minus 1s with a 2. So if I were to rewrite this, taking this, 2 minus 1 over 6, get rid of the pole, z to the minus 1, oh, there you go, z to the minus 1. Where we replace all the z to the minus 1s with a 2. Don't forget this. If you forget this, you're going to get some really, really bad numbers. So replace 2 minus 1 over 6 times 2, and then 1 plus 2 over 3. Okay? And that's going to equal, well, that's going to be 2 over 6. That's going to be, I'm going to do 12 over 6. means 12 over 6 minus 2 over 6 is going to be 10 over 6 divided by, that's going to be 3 over 3, 2 over 3, 5 over 3, okay? And then, because I like doing the math like this, let's flip this, 3 over 5. This just becomes a 2, and then this becomes a 2. Cool. That's our A coefficient. And now our B is going to equal, okay, where's our pole? Write your pole at minus 1 over 3, okay? But your z to the minus 1 is going to equal to minus 3. Don't forget. So that means rewriting all this, 2 minus 1 over 6 z to the minus 1 divided by, remove that pole, 1 minus 1 over 2 z to the minus 1, okay? Is equal to 2 minus, well, plus 3 over 6, okay? 1 plus 3 over 2, okay? And yeah, let's keep going with this marker. It's going to be 12 over 6. That means it's going to be 15 over 6 divided by, and this one's going to be, that's 3 over 2. It's okay. 2 over 2, 5 over 2. I'm going to rewrite it like this, 15 over 6 times 2 over 5. This right here cancels out to give you a 3. And then this right here cancels out to give us a 3. Like these problems? Why? Because I made that. Could be on the final. Cool. All right, now let's rewrite it. So this is page 6. And now let's get to page 7. Okay. And now we can write the following. H of z is equal to 1 plus 1 divided by 1 minus 1 over 2 z to the minus 1 plus 1 plus 1 over 3 z to the minus 1. We're done. Not yet. Now we got to convert this into h of n. So what's the inverse Laplace transform of a constant? A delta function. Okay, well, it's 1 and delta n. Cool. Now plus, okay, what's the residue? 1. What's the pole? Pole's at 1 over 2. But we have to do this. Put these parentheses in there. To the n, u of n. Cool. And now our final term, 1. And then this pole is at minus 1 over 3. Okay, u of n. And there you go. Who's ready to prove this in Matlab? So, you see that right there? So, one question is, what happens if, before I were to keep going, what happens if you had the following? And maybe I'll just kill 2 birds with 1 stone. Here's your unit circle. Oh, I just draw it like this. But instead of it being inside, what happens if you had it outside? Like at minus 3. Okay? You have a pole this way. To make it a stable system, you have to go inside and non-causal. So left-sided. So that means if you were to do something like this, if you were to try to make it stable, so let's say res divided by 1, and you have a pole at 3, okay, minus 3. That means this would turn into minus residue minus 3 u of minus n minus 1. Cool, and that makes it non-causal. There we go. Nice. Oh. All right. So now let's prove this in Matlab, and I got a nice example for everyone. Let's see. Boom. And before I even look at that, let's just redo the assignment again, if you think about it. So, yes, you can also use Matlab for not just the homework. The whole point is you can use this lab, this digital lab, to analyze any system. And the following system I have for you is this. H numerator, denominator, set up this, set up the power, don't forget it's log 10. Easy, easy, easy. And then I did this as our Fourier coefficients because we're gonna do the freaks function. Don't forget that. And then I drew this circle here. What is that? Z. What's Z? Yeah, this is just a circle. Drawing a circle. Drawing a circle. And then if you run that, and then I put the Z limits because it goes to infinity. What happens if I cut this off? Okay, I'll show everyone. Control. Come on, Matlab. See that? Cool, right? Oh, Matlab, don't die. Nope. See that? Cool. But look at that spike. That's a big pole, so we don't want to see that. So that's why I put the following. And let's decrease the precision. Let's just run it again. There you go. Now we're bounded. Cool, right? And if we were to go above, look at that. Does that look like our diagram that we had? So I'm going to pull this guy. See that? We have 2 poles, and we have 2 zeros that are tucked inside these poles. And minusing that. See that? Getting your money's worth? Cool. And then, oh wait, let me run that again. See that? Oh, what's that purple line? And where's the black line? Oh, I know where the black line is. It's located at 30. So if you wanted to, let's put it at 15. There it is. That's your unit circle. Ah, cool, right? And now let's go to this one, and that's just doing the Fourier, looking at the imaginary axis. Cool, right? And that pink line or magenta line is that, just wrapped around it. And let's see, what type of filter response is this? Someone could judge this as an all pass. There's a gain too. Look at that gain, DC gain. Like if you think about it, when there's hardly no phase, the phase just jumps from 10 degrees and minus 10 degrees. Okay, it's okay. Don't worry about the system response. But that's how you do it. And then, where are our poles and zeros? Where are the poles and where are the zeros? Actually, where are the zeros? The zeros are located at okay. And then where are our poles? There you go. You see, you can check your answers. Okay, and then TF to ZP. Oh, I know what this is. I don't know why I put that. See that? Look at that. That looks like our diagram that we drew. Okay. And then here's the residues function. So this is really important. Okay. So enter. So look at these numbers that pop up. RPK. So R just stands for the residues. What's the residues of, okay, so this right here is what's the residue of the first pole. The first pole is at 1/2. And what residues does that pole residue? It's 1. Okay, and then what's the residue of the second pole? 1. Where's the second pole located at? -1/3. Okay, and but what's this K value? Does that bother you? help, residues. And what it's doing is this. Here's your partials, right? Here's a partial, and look at that. That's your delta function, okay? So if you wanted to plot this in the time domain, okay? You know that here's your hand calcs. Here's your hand calcs, right? You can program this, okay? How do you program something directly from Matlab? You didn't do any hand calcs. Matlab does all this for you. Like look at all this pain, right? What if you wanted to get right to this answer without doing all that pain? Listen to Matlab. Matlab's telling you, let's see. Okay, David, I have 2 poles. Okay, that's all you need to worry about. I have these residues, and I have this delta function. That's all it's saying. So that means if you wanted to plug it in, you have 3 things to plug in. Okay, plug and chug, I guess. Read the residues. So from 0 to 50, we have to have a delta function. And when does the delta function begin? It begins at n is equal to 0, okay? So that means whatever number we get from there, k is 1, right? And then we just add zeros. Easy, right? And then here's our residue. Here's our pole to the nth power. Ah, okay. And then let's see what this puppy pops out. Cool, right? And don't forget the title. Someone's not titling this class. Title. Impulse response. Using and calcs. There we go. There we go. Oh, and okay. X label n. And now for the step response. I'll show you that. So to do a step response, don't multiply the step here. Don't do that. That's really bad. What you're going to do on the exam is go back to this. So Dr. Stuber said there's a student who's using this final answer, and then they're convolving this with the unit step and this with the unit step, and they're doing 2 partial fraction expansions. No, don't do that. Don't do that. What you're going to do is you're going to convolve it with this, okay? Well, kind of not that. Well, you know how to get these poles, right? All I'm going to say, if you wanted to step response, u of z, okay, x is equal to, x of z is equal to u of z, which is equal to 1 minus z to the minus 1. Okay, so you're going to multiply to this h of z, h of z, u of z. Okay? And don't multiply this. Multiply it to this. So if no one's watching these videos, all right, now you know the trick, okay? And then you can convolve these denominators, this denominator term, denominator 1, with denominator 2. And that's what I show you right here. So here's the numerator, here's the denominator, okay? Here's 0, here's the 1 coefficient, this is z. Here's 1, and then here's, is that how I want to show it? No, this is the ones place. This is also the ones. Actually, okay, I'm going to do the comment. Z and a constant. Oh, nope. And then this one right here is also z const, okay? No, wait, nope. I'm writing it backwards. Constant z to the minus 1, z minus 1. Cool? And then you just convolve. Easy. And there's nothing to convolve with the numerator because it's just a constant. wrote this backwards. 1, 0. Something's telling me something's not right. Oh, there it is. Okay. Then when was it given to me? Residues, y of n, u of n, d. Maybe I wrote it wrong. Let me see. 0, 1. We will verify this at the end. 1, 0. See how similar that is? But yes, that is a step response. And ooh, look at that. DC gain. I'll show you that at the end. Now, we can proceed to the second half of the assignment. So, for the second half of the assignment, let me pull that out. You're going to be using the controls toolbox. And what I asked for problem 8 is to draw a direct form block, and I would assume everyone's a master of that, but because I'm running out of time, okay, you're gonna do a direct form 2 block and then solve for all A, B, C, and D, okay? I want to see all the hand calcs, and someone's probably not getting the memo. I'm not grading the code, I'm grading, do you understand what's going on? Please, submit the hand calcs. Those are worth a lot of points. So, like, oh, David, I did all these problems. Yeah, they're literally one-liners. As you can see, they're just, well, kind of one line. I'll show you the rest of the assignment. It's literally one line, and it's really simple to code. Once you get it, it's really easy. So I'm not grading crazy on this, but you got to do it and understand what's going on. But I'm grading heavily on 8 and 1. Okay, can you do this? Can you perform this on the exam? Yes or no? Easy. So for number 9 is what you're going to be using to verify your answers, and that's what I did right here. Verifying your hand calcs. And then you can use this EQT, equal length functions. It makes your numerators and denominators equal. So if this was like, I don't want to do that. Nah. Point is, if one of them was off by a value, and I'm going to tell you all the denominators would be off by power, so the denominator would be a greater power than the numerator. This function just basically fixes your numerators, okay, to get you the following. And there you go. So if we were to do a state space representation of our quiz, this is the answer. Easy. That's how Dr. Stuber checks your answer too. Like, if he were to give you, let me show you this on a quiz, but not as a block diagram, not as this. Well, he says derive the block diagram and derive the state space equations. Your answer is just this. That's it. Really easy. So once you confirm that, then you can proceed to continue the lab, and then use the state space equation, AZ, BZ, but put this -1 there. This turns on the discrete mode. So if you don't, let me show you. Boom. And that's definitely not right. Don't worry about that. But you see, it says continuous time, okay? But we want discrete mode. -1 turns on discrete mode. And there you go. Hey, does that look like something? Let me pull that out. 22. Actually, no. There's another way of doing it. That's figure 22. Figure 222, right? 222, right? That's our figure. And where's the other figure? Okay, figure 2. Cool, right? Calling the other figure. Oh, it won't let me call 2 figures at the same time. Hold up. Figure 2. Ah, it does work. So this is from the first part, and then this is the state space equations. Do they match? Congratulations. Now you're getting somewhere. And now, oh yeah, for this one, I should make an announcement about that. You should be using the squeeze function. So what freq response does is it gives you the following, and I'll show you what it does. F9. Oh, no, don't want to press that. F9. And it gives you this. It's going to give you a 1 by 1 by this many points. Don't worry about that. Actually, you should be worried about it. But point is, Matlab doesn't like this. It's not going to understand this. So what you're going to do is, well, squeeze, okay? And I should probably make an announcement on that. And if you were to squeeze it, F9, now it turns it into 1 by n length. Well, however long this W is, okay? Actually, yes, the W. However long W is, and it'll give you that. Length of W. Into length of W. Cool, right? And then semicolon, and do not forget the semicolons. And then do the assignment as you like, and there you go. Simple. What are the poles, zeros, and gains? Run. Oh, look at that. Cool, right? And oh, what is that 3.75? So this is a number, and remember from the last assignment, I was saying, what's the DC gain of your thing? So what I'm going to tell everyone is the following. 7, 8. Okay. Let me write this on a piece of paper. Okay. Let's pull out the following function that we had. H of z 3 minus 1 over 3 z to the minus 1 minus 1 over 6 z to the minus 2 1 minus 1 over 6 z to the minus 1 minus 1 over 6 z to the minus 2. Okay, and what we're gonna do is a DC response. So what is this function's value at DC? So if you remembered from what I did in the last class where you were doing the Fourier transform or J omega. So, actually, do I want to do that? Actually, okay. Where we were looking at purely this circle, right? Well, where's DC? DC is located right here. Okay, so what value is that? All right, so that means if you were to look at that point, like whatever that function is, here's 0. So I mean that's equal to DC, okay? So all you're gonna do is when z is equal to 1, just replace everything with 1. So that means to get the DC gain, you're gonna do the following. So that means 1, 1, 1, and 1. 3 minus 1 over 3 minus 1 over 6 divided by 1 minus 1 over 6 minus 1 over 6. It's going to give us the following. This right here is, actually, do I want to do that? Actually, okay. This right here is 6, and that's a 2. That gives us 3 over 3. No, 3 over 6. That means this right here is going to be 18 over 6. Is that correct? It's going to give us 15 over 6. Okay. And then this right here is 6 over 6. It's going to give us 4 over 6, which is equal to 15 divided by 6 times 6 divided by 4. It's going to give us, well, how many times does 4 fit into 15? 3 times with 3/4. So if we were to look at DC, and actually let's look at it, 20 log 10, 3.75, what is that equal to? Let me show you. There we go. 20 times log 10 of 3.75 is 11.48. Is that what we're getting? 11.47. Close enough, right? Cool, right? You see, all this lab, this is a digital lab. Everything you're getting from this, you can apply it to any system, and you can analyze any system at all. So, is this making sense? Cool. And now let's look at PZ map. Look at this. It's just one line. I'm literally doing your assignment. Does that look like the first thing we did? Here's your impulse. This is how you do it. And look at that. Ooh, cool, right? And actually, let's compare this to the first plot. This is 420. Here's the step response here. And let's pull out the last figure. Do they look the same? Cool, right? Here's a 3. That right there is 0.361111. See? Make sure they're matching. If the first half's not matching the second half, then something's wrong. Check your work. And it's most likely the first half. Well, I doubt the second half would be. As long as the only problem I would see is this is wrong. If this is wrong, then please check that. This is never wrong, or unless this is wrong. This is where the mistake would come from. But please make sure you check the first and second half. They all should match. And then here's your step response. Just step. Okay. And look at that. And let's compare this to the first step. Step response. And then, where's that step response? And look at that. Do they match? Yes, they do. 3. So that means what I did here, yeah, that's correct. Actually, let me show you the mistake that I was doing. Don't do this. 0, 1. Okay. See, this is from the first half, and you see that big weird. Actually, no, I think they're the same. Are they the same? No. You see that 1? That's gone. You see, that's bad. Okay, so it should be this 1, 0. There you go. Now it fixes that, and then both fixed. Easy. And then I'll just let you guys do the last part for homework, and that wraps up the entire assignment. This should be probably one of the easiest assignments. And see that line right there? Yeah, I put in there that for a reason. Please, I want to make sure you guys are understanding this. Like these assignments. Well, if you're understanding this, I'm really happy for you. But please, like I'm giving you an extra problem here. You can do it with any book problem you have. Okay, and use this impulse, use these step responses, DC gain, analyze this. This is going to help you a lot, well, for 480. Everything you do in 480, everything we do here, you can apply it to 480. This is the digital lab. The other one was the analog lab, and let me show you. Yeah, that's about it. Okay, so one last thing before I want to end everything, and I should probably do the following control. CLC, clear all, close all. There we go. So one thing I need to explain to everyone. Should we do it on another piece of paper? Yeah, I will. Getting your money's worth now? Not enough. 9. So, for the Z transform, remember how, actually in the Laplace transform, where we were doing, we had Q of T, this Q of T, right? We had a vector Q of T, right? Remember that stuff? It's equal to AX of T plus B Q of T, no, Q X, there we go. Then Y of T is equal to C of Q of T plus D of X of T. Remember that stuff? And we wanted to turn this Q of t into SQ t. Remember that? Q of S. Remember that? So same thing with the Z domain, Z transform, where instead of this derivative, we're going to have Q of n plus 1. Okay? Plus 1 or minus 1? Is it going to be a plus? I remember. Is it plus 1? Show that this and that, this and that. Okay, let me remember this. Should be a plus or should be a minus? Well, since we're dealing with next states, Q of n plus bx of n, y of n is equal to cq of n plus dx of n, where remember how we were doing, q of n minus 1 converts to z minus 1 q z, right? Remember that? So that means if we have a minus here, here's a minus, that means this should consequently be q of z, z. Right? Hopefully that's correct. Well, because we are dealing with next states, so should be the same topology. Then you would solve for, well, you would solve for q, z, and do all this other stuff. I'm not going to go over that mathematics. It should be the same methodology, so do expect the state space equation, and then he's going to give you, okay, prove this. Okay, prove. And you should be able to prove the following. Oh, there it is. Y of z is equal to c of zi minus a minus 1 b plus d x of z. Okay? That's everyone's homework for today. So prove that on your own. And anything else? You're going to have initial conditions. So remember the first half of the assignment. This right here. Don't forget your ZSR, ZIR stuff. Shouldn't be that bad. Where is it? This stuff. You're going to have that on your exam. Just punch a number. This is probably going to be a... Maybe this might be a 0, 0. This might be a 1 or something like that. Same thing. Do the polls. Easy stuff. And yeah, that's about it. Don't forget stability. Understand your ZIR, ZSRs, and your state space equations. And this should be a easy exam. And then the assignment, everyone should be easily finishing this assignment pretty soon, pretty fast. Shouldn't take you more than like an hour. And yeah, with that, actually, let me just outro it like this. This is the final one. Page 10. So, CA5. So you've already experienced the analog domain. So all this analog stuff you were doing was all like EE370. So everything we've done in that analog lab, you can do everything. You can do your S's, you can calculate your... Actually, there's one thing I wanted to show you. This is very important too. Let's go back to that one plane. Verify the hand calcs. This. Running. Let me show you this plot right here. There's one important factor that you can see with both the Z domain and the Laplace domain. You see this right here? I'm going to click on this. You see that number? It says, oh, pole damping factors and overshoots. Let me show you this. See that right there? Overshoots. Ooh, and then it gives you a frequency of that pole too. Cool, right? You're going to see that a lot in 370 and not so much in 480, but definitely in 370, like, oh, damping factors and overshoots. So that's where all that comes to play. So have fun with that, and then you can also do like Bode plots, circuits, and op amps. Just like analyze op amps. Like, you ever design an op amp? So like 420 applies to this too. 420 EE360, where you start building like these big fat op amps, and then you see like another pole right there. This is like your F3dB. Here's your AOL gain or something like that, and this would be your F unity. Remember that stuff from like 320 lab? Like, this is where you would analyze like if you were to hopefully take Dr. Baker's 420 class, hopefully one day, you can analyze everything using this computer assignment. Don't forget it. It's going to ring in someone's brain. And then computer assignments, let's not use that marker. CA6 is the digital lab. And that's purely EE480. And then the other class I recommend is ECG 722, which is mixed signal design, circuit design, where you're going to be designing a lot of stuff. You're going to just be looking at like, oh, these like cool poles that like do something like this. Like, oh, here you have a circle here, you have a circle there, you have a circle there, and circle there. This is basically a linear FIR or something like that. You're going to see stuff like this all the time in 480 and 722. And then everything we've done here, you can analyze this right there, and you can look at Discrete-Time, Fourier transforms, which is basically the unit circle, everything. And then what's the other thing? And I guess you can use like ADCs. Not the other ADCs from a game, but ADCs, like, oh, here's your 1 over f of s, and then here's your analog to digital, here's your x of t, and then this would be your x of n t, something like that, and then it would be a sine wave, and this would be like like something like that. Digital, pretty cool, right? So that wraps up the entirety of this class. If you really enjoyed this stuff, well, I'm glad to be your TA for this semester. Really fun too, learning all this stuff again, but hopefully everyone will do great on this exam, on the assignments, and in the entire class in general, and whatever you guys want to do. So it's definitely been a pleasure, and I think with that, yep, any other questions? Chat, we're doing good? All right, everyone. Have a good day.